one of the best ways to get to know Euler's method is to just graphically understand the method. And that's what we have planned here. This is basically going to be approximating an Euler's method approximation, but that's okay. Understanding graphically is the point. Alright, in the upper left there's a differential equation that has a boundary condition. This is just the kind of differential equation Euler's method is very good for. It's a first order differential equation and it has an initial value. Okay, now Euler's method provides a polygonal curve approximation. That means the approximating function provided by Euler's method is a concatenation of line segments. That being the case, we first have to decide how long the line segments are going to be, and it's actually the change in the x direction that you decide, which is called the step size. So for purposes of this example, we will choose to have a step size delta x equals 1/2. And to help us see our step size, so we can do this, we'll put some grid lines on our coordinate system here. We'll put vertical lines on spaced every 1/2 unit in the x direction. Okay, there they are. Now another thing that we need to do our purely visual Euler's method here is we should have the slope field of that differential equation. Imagine it didn't have the boundary condition, just the dy dx equals y plus xy. What about the slope field for that? We would like to have that too, because that'll help us decide how to direct each of our line segments. So we'll superpose the slope field as well right now. Okay, this is enough to get started. Now, the only thing we know to graph exactly at first is the initial value point. So there it is, -2, 1. Okay, let's start creating our first line segment to the Euler approximation. We're going to begin at the known point, and now we want to use the slope at this point to direct our line segment. So I sort of look at what that slope field seems to have in mind for a slope at that point, -2, 1, and I think it's about like so. And when I get to this grid line, I know that I now have a delta x of 1/2. It's time to terminate the line segment and begin the next line segment of this Euler's method approximation. This line segment begins at this point, and now I look at the slope field. I try to figure out what is the slope at this point that directs my next line segment. It looks about like this, and I go out as far as till I hit the next delta x equals 1/2, and that's where I need to terminate this line segment. And there's a second one. A third line segment begins here, and now look to the slope field to see what the dy dx value is right here approximately. Looks about like so. Terminate that line segment and begin another one. Looking at that slope field to direct ourselves, it looks like we go slightly about there, and then begin the next line segment at this point, watching the slope field for direction. Looks like we should be heading over about like so, right there. And well, I guess we'll stop doing anything else here, and to provide a contrasting color, let's get that set up here. Okay, so here is our graphic construction of an Euler's method. This is actually an Euler's method approximation over the interval -2 up to +1/2, and the step size is 1/2. And we did this just all based on visual graphic process. just to try to understand the method. This is basically what it does, though. Just for fun, try another Euler's method approximation. This time, let's try to make the step size 1/4 instead of 1/2. So, to help us out for this, let's put in some grid lines every 1/4 unit in the x direction. Okay, we have that. Let's start again. Okay, we go to our one exactly known point right here, and now let's start a segment. Now this would be exactly the same as the first approximation, except for it stops here when we've traversed 1/4 unit of x direction. Now we start a new line segment, and looking at the slopes, it looks maybe about like so, and terminate and begin a new line segment. Looks like it would be about like so. Again, looking at those that slope field to try to figure out how to direct the line segment. Terminate it, begin another one. Watching that slope field. About there. Start another one. About there. Start another segment. And terminate. Start another segment. Terminate. Start another segment. Looking at that slope field, this one about like that, and start another segment. Watch the slope field at that point to determine the direction to go, about there, and start one more segment. About like that. Okay, let's give this Euler's approximation another distinctive color. Let's go for green here. Alright, so there in the green is our graphically drawn Euler's approximation with a step size of 1/4 over the interval -2 to 1/2. Alright, now as it would turn out, there is an exact solution to this differential equation, and just for additional information, let's try superimposing the exact solution graph over these Euler approximations and see what it looks like. Alright, so here we have in the blue the exact solution graph, and as we see, the Euler approximation does okay in the beginning, and then the error does tend to accumulate here. You'll notice another result, and that's that the approximation with the step size of 1/4 did a somewhat better job than the step size of 1/2, which is kind of typical. You see, if you just move smaller increments at a time and change your direction, chances are you're going to do a better job of following the true solution curve. And also notice that when you do have your direction of the line segment, you are just using that dy dx formula at some point in the plane. You are, with the exception of the first point, probably never on the actual solution graph. You're never using a tangent line to the graph of the solution itself. You're almost always using tangent line slopes to other solutions of the general differential equation. So anyway, there's a couple of approximations just done off of a purely visual basis to get to know this Euler's method. Okay, now that we've seen a couple of Euler's methods approximations created just by working off of visual graphic ideas, let's try to turn this into some algebra as well. So here we have a snapshot of our first Euler's method approximation, at least part of it, and let's take a look at this again. We could label this first point as x sub 0, y sub 0. Here was the first point at the end of a segment. We can call that x sub 1 y sub 1. Here was a third point, I suppose. We call that x sub 2, y sub 2. Alright, now what about formulation for the y coordinate on a line segment here? More specifically, the right-hand y coordinate. I don't want to work off of this line segment because this one is really special compared to perhaps everything else in the Euler's method approximation. Why do I say that? Because here the slope was determined by dy dx at this point, which meant this slope is actually a tangent line to the actual exact solution, which is also put here, superposed here in the blue. Okay, usually you are off the exact solution in the middle of the coordinate system somewhere, and your dy dx merely corresponds to a slope to some solution, to one of the family of solutions to this differential equation without this boundary condition. Okay, anyway, let's start here. Let's take a look at this line segment here, for instance. What can we say about this? If we took a look at this line segment, it's a straight line with a couple of endpoints, so we could simply say that the slope of this, using the traditional two-point formula from algebra, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay, now the slope, what about that? Okay, that's where we're using the dy dx formula, substituting in the coordinates of this point. So that is, algebraically speaking, a dy dx evaluated at x sub 1, y sub 1. On this right hand side, this x sub 2 minus x sub 1, that's the difference of the x coordinates, and that's actually something we know right away because we decide that ahead of time. That is the step size. So right here, this is the step size, which we can denote as delta x. Okay, so let's rewrite what we have here based on this input. We've really got dy dx evaluated at x sub 1, y sub 1 equaling 2 y sub 2 minus y sub 1 over delta x. Okay, now the thing you need to genuinely compute in an Euler's method approximation is the right-hand y coordinate. Okay, so y1 is actually known to us because we've already gotten to this point. But y sub 2, the future y coordinate, is what's unknown. Well, we can, of course, solve this algebraically for the y sub 2, multiply both sides by delta x, add a y1 to both sides. This can become, put y sub 2 on this side now, equal to y sub 1 plus dy dx evaluated at x sub 1, y sub 1 times delta x. Now, what we have here for this particular line segment really is done repeatedly throughout all the other line segments. It's just that we are computing for a future right-hand y, which always has an index 1 greater than the y of where you start from, and so this generalizes to a y sub n plus 1 equaling y sub n plus dy dx evaluated at x sub n y sub n times delta x. And this is the basic algebraic formulation for Euler's method as you go to generate all your y coordinates for each segment. Okay, ready to go ahead to an exercise question now. Alright, 1a. For the differential equation dy dx equals 2x minus y plus 1 with y of 0 equaling 2, manually sketch the Euler's method approximation having step size delta x equals 1/2 over the interval 0, 2. include labeled exact coordinates for each line segment endpoint. Alright, an Euler's method approximation. It's a polygonal curve. It's a concatenation of line segments. So we would need to start at our first known point on this curve. That is the y of 0 equals 2. Okay, the point 0, 2. And from there, start generating one line segment at a time. Okay, I think setting up a table would probably make this easiest. Alright, so I want to keep track of these important points, endpoints and line segments, calculate them. And so we have here an x sub n and a y sub n. And then when we have a point, we need to decide which direction to go. So then we'll also need to be calculating dy dx evaluated at x sub n, y sub n. And we have right here a formula that we can use for that. Once we have our direction in mind, we can go to the next y coordinate, y sub n plus 1, and that will become y sub n plus dy dx evaluated at x sub n, y sub n times delta x. Okay, the first point we know of is this 0, 2. Okay, so from there, which direction to head? Dy dx, here's the formulation. So substituting the 0, 2 in there, 2 by 0 minus 2 is y, plus 1 looks like negative 1. Okay, so our y sub n plus 1 will become, the original y here is a 2, and then plus slope times delta x. Step size is 1/2. Okay, this adds up to, let's see, 2 minus half, 3/2. Okay, by the way, the x's here, since we know the step size, this column can be completed right away. So we could have a 1/2, 1, 3/2, and 2. And just n is 0, 1, 2, 3, 4. Now we know the next y coordinate for the second point here, 3/2. Okay, now back to, now that we know we're at this point 1/2, 3/2, let's get the new direction to head based on this formulation dy dx again. Here it's 2 by 1/2 minus 3/2 plus 1. Let's see, 1, 2 minus 3/2 down to 1/2. Okay, so now it's the original y, 3/2, plus slope times delta x. Okay, 3/2 and 1/4. We're in the world of fourths here. That's 6/4, 1/4, 7/4. And that gives us the y sub 2. Okay, so this point 1, 7/4 is an endpoint of one of the line segments. Which direction to now head? Okay, back to dy dx. 2 by x is 1 here, minus 7/4 is y, plus 1. We're at, let's see, 2 minus 7/4 down to 1/4, plus 1 puts us at 5/4. Okay, and now the actual next y coordinate, let's see, original y, 7/4, plus slope times delta x. Okay, we are in the realm of eighths here, 5/8, and this would be 14/8. 14 and 5, we're at 19/8. Okay, and that's our y sub 3. Okay, now which direction to head once we're at this point here? Okay, back to the formulation. 2 by x is 3/2 minus the y, that's minus that 19/8, and plus 1. Okay, so here is actually 3 minusing 19/8. Okay, 3 is 24/8 minus 19/8, 5/8, plus 1, back up to 13/8. Okay, next y would be the starting y, slope, times delta x. Okay, we are in the world of sixteenths here. 13/16, 2/2 buildup. This is a 38/16. 38. Let's see, 38 plus 13. We're up to 51/16. That is our y sub 4. Okay, well, we have these endpoints of all the line segments ready to put together our graph. Let's see what kind of coordinate system we need here. X is going from 0 to 2. The y's range here from 2, well, 3/2. Okay, I'll say 0 up to a little more than 3, 0 to 4. That would be enough y-axis to fit everything here. Okay, let's put together the coordinate system. Alright, so I've got these axes here. Label this axis as x, and this axis, we're going to be graphing a Euler's method y of x is on this axis. Okay, and let's see here. Up here, our first point, the known starting point, 0, 2. There, and then we have 1/2, 3/2. Okay, 1/2, 3/2. There. 1 7/4. 7/4. It's almost 2. Let's put this here. Okay. 3/2, 19/8. 19/8. So let's see, 2 and 3/8. Okay. 2 and 3/8 would be about like so. And then 1, 2, 3. There. Okay, and then 2, 51/16. 51/16, that is 3 and 3/16. Okay, about there. And 2 for x, about there. Okay, now, important, got to have a straight line segments connecting these points, right? That's what Euler's method is all about. Concatenation of line segments. Okay, and let's label these coordinates here now that we see how to label without getting in the way of our graph. Here, 0, 2. Here, 1/2, 3/2. Here, 1 7/4. Here, 3/2, 19/8. And here, 2, 51/16. And maybe a little touch of white out right there. Alright, about like so. There's our manual graph of this Euler's method approximation. Again, it's right now it's rather error prone. There was a lot of tedious arithmetic that goes into this, so fortunately we have part B of this question to get some consistency evaluated. So we'll go to that next. 1b. For the same differential equation, dy dx equal to 2x minus y plus 1, with y of 0 equaling 2, use the TI-Nspire to sketch the same Euler's method approximation. That is, step size delta x equals 1/2 over the interval 0, 2. Then assess the correctness of parts A and B by examining for consistency between these two solutions. Okay, let's bring out the Nspire. Let's start up a new document. To get an Euler's method approximation, we'll need to work that in a graphs application. Alright, we see the usual default entry line in a graphs application is the function. We want to do something differently here. We want to be in the differential equations edit screen. So let's go to the menu, and as our graph entry choice goes, let's go down here to number 7, go with differential equation. Alright, one thing you see here, and that's that it has a name in mind for the function as y1. You can change that if you want to by clicking here and putting in your own name. Probably resist using just a simple y in the Nspire, so we'll stick with the y1 they've chosen here. And notice this line does not say the y1 equals 2. Look closely, there's a prime, it's a derivative, so this is a derivative of y1 formulation here. Okay, from our differential equation we have dy dx equal to 2x minus y plus 1, so let's put in here a 2x minus, and here's a point to be careful of, as the Nspire is using the name y1 to refer to the function, not y. We need to be consistent, and you can't just put a y here, it needs to be y1 also. Okay, and then plus 1. Let's arrow down here. Here's a place to put any initial value we may have. Since we have y of 0 equals 2, that means 0, 2 is on the graph. So 0, tab 2. Okay, now I will arrow up and tab. What's this little item here that's been delineated? There's the edit parameters. Okay, let's do that. Hitting enter. Now, for our differential equation, we have some things to select. Solution method. Yes, we're using Euler's method right now, so let's keep that. In case you're wondering, we have another choice, Runge-Kutta, which we will use later on in this exercise. But right now, Euler is for us. Okay, tabbing down. Iterations, just keep that at 1. We do not want any field in our background right now. I think I'll just strip all that away. Just have our Euler's method function being graphed. That's it. And leaving the axes alone. Tabbing down, tabbing down. Okay, the plot start, we're over the interval 0, 2, right? So we'll make our plot start here to be 0. Plot end, 2. Our step size, plot step here is step size, and we've chosen 1/2, so we'll go with 0.5, tab, and hit OK. Alright, so here's what we start off with. Let's see, first thing we could do is we could make this graph entry line go away with an escape key. Now, I think I'd like to be labeling this as an Euler's method approximation later on, so I'm immediately going to just take this label that they put here and delete that. This graph is quite congested right now. I want to spread things out a bit, so a good chance to go with menu, window zoom. I think I'll use zoom box. Upper right corner, maybe about there, say. Coming down, want to get the x and y axes in the image if I can. So perhaps there. Okay, let's see, I think I'll put that tool away, escape, and let's see what else here. These axes are scaled in a rather congested manner right now. I think I'd like to change that a bit, so let's go back to the menu. Let's go to the zoom, window zoom, and window settings. Let's see, X min. Maybe just make that a -1 for simplicity. X max, maybe a rather simpler 2.5. X scaling, I think 0.5 would be nice here. Y min, okay, maybe negative 0.5. Y max, I'll say 4 perhaps. Scaling, okay, 0.5 as well. Bringing us to here. Alright, this is looking better. Now, one thing we know about an Euler's method, and that is it is a polygonal curve. When you talk about the function that's being approximated, right now we just have a collection of 5 discrete points. So let's help out the Nspire a little bit here. We need some line segments. So we can go to the menu and go to geometry, and points and lines and segments is for us. Okay, just have to connect the dots. Pretty easy. One click to start a segment. Go to where we get the point there. Click to terminate, and then click again to start the new segment. Click to terminate it. Click to start a new segment. Click to terminate. Start again. Click to terminate it, and escape. Put away that tool. Now, I always like to have the graphing object be a contrasting color as compared to the background coordinate system. So I'll fix that up a little bit here. I can go with start selecting the point, the segment, this point, that segment, and so on. And now go to color, align color. How about red? Okay, looking better. Let's see, still don't have the label of what is actually going on this y-axis here. So for this, I think I'll go to a menu, actions, bring up the text tool. Okay, I want to put Euler's method approximate y of x on this y-axis here. And so I think to do that, I'll start up a box here, and Euler's. Now because I want this all to fit on the left, to the left of the y-axis, I'm going to just do it in separate text boxes and then fix it up. Okay, so there's a clearly labeled y-axis. We are graphing an Euler's method approximation of y of x. Another item needs to be taken care of, and that's we are supposed to have the coordinates labeled on each point here. So that's not hard to do. We can go to it and go with coordinates and equations, and each point, same kind of command. Okay, now maybe put these labels in clearer locations. Okay, there. Now, another issue is we do want to compare this to our manual graph. The trouble is, when we did our manual arithmetic, it was of course easiest to work with fractions, not decimals. Here in the graphing application on the Nspire, it's pretty much an all decimal environment. But if we get a table, the table is actually part of the spreadsheet application, which can be made to be exact. So let's do this. Let's get a table going. Control T. Alright, now the table puts itself on the very same page as our graph. Myself, I like to spread things out a bit. So to make this table go to its own page, I'll go Control 6. Okay, let's go to that second page now. Here's this table. Let's see, a couple little obstacles for us. One is, notice that the x only goes 0, 1, 2, 3, 4, 5, 6, which is the default increment for the table, x every 1 unit, but we need x every 0.5 units. No problem. We can just go to the menu, table, edit those table settings, and let's see, table start at 0 is fine. Let's tab down, to the tab step and make that a 0.5. Okay, everything else is in order. Click on OK. Okay, great. Now we have coordinates for each of the same points we graphed manually. But our last remaining issue is that we would like to make a comparison here between our manually tabulated exact points and these decimal numbers here. So to clear that up, we could do this. Let's go to check the document settings. And right now the calculation mode is in auto. Alright, so to force exact fractions on this table, let's change that for right now to exact and click OK. Then just re-click on one of the cells and automatically it will change over to this nice exact form for us. And with this exact form, we compare to our manual tabulation, and it appears that indeed each of these coordinates is exactly the same as we got manually. Okay, so I'll take a couple of screen captures here. Okay, and now I can take these captured images and put them onto the original exercise set. Okay, so returning to the exercise set, I took those captured images and cropped them a little bit using a Microsoft Office application and pasted them here into the exercise set. So we have the graph on the left from the Nspire and the Nspire's table on the right to help show us exactly what those coordinates are. And we can compare that to our manual graph and see that it's basically the same shape except for some compression of the y-axis on the Nspire. And we furthermore see that the coordinates are identical by using the table on the right, comparing to our manual table calculations. Okay, I'll write that down. Alright, there we are. Assessment. By taking into account the compressed y-axis on the Nspire graph, we see that the manual graph and the Nspire graph are the same. Furthermore, by using the Nspire table of coordinates, we see that they are identical to the manually computed coordinates. Thus, the manual calculation and the Nspire calculation are consistent, and consequently, parts A and B appear correct. Okay, let's go to part C. Okay, part C. For the same differential equation, dy dx equals 2x minus y plus 1, with y as 0 equals 2, consider the specific problem of approximating the function value y of 2. Using the Nspire, obtain Euler's method approximations by using step sizes 1/2, 1/4, 1/8, 1/16, and 1/32. Organize this information into a 2-column spreadsheet. 1 column for step size, a second column for the corresponding Euler's method approximation of y of 2. Okay. Alright, we last left off with this graph of a Euler's method approximation. And for what's at hand here, a specific value, maybe we leave this all here intact, and let's maybe go to another page, go with the graph, and return to the entry line for differential equations. Arrowing up. Okay, it actually still has the y1 from the first page in there, and a couple points here sitting here in graphed. Let's escape to get rid of that line. We won't need this label at all again. Maybe we make these points here a little bigger. Zoom box again. Maybe there. Down to, say, there. And escape to put away that zooming tool. Okay, now here, again, the concern is simply one specific value of the y of 2. If we go here, if we pull up a context menu, Okay, we don't have the coordinates option available there. Okay, no problem. Something else we can do. Okay, we could try a graph trace and then hit enter when we're on this point here. Let's try that. So menu, trace, graph trace, and let's arrow over here because this point has an x equal to 2 on it, and hit enter. Okay, escape to put away that tool, and this point here, maybe just a slight maneuver. Alright, here's what we want to focus on is this y coordinate here for various Euler method approximations. To get good control over this, it's probably a good time to make this into a variable. So here, put up the context menu, and let's go with store, and let's call this the, let's see, approximate y of 2, so APPROX, and since this is a variable name, you can't leave blank, so I have to go with underscore, y, can't use parentheses, so it's y1 of 2, like that. As a variable name, we can't use parentheses either. Okay, so we got that labeled as a variable there. Now, I suppose it's a good time to start setting up our spreadsheet to collect these various errors. Okay, so let's go with control, add a page, and let's add a list in spreadsheet. Okay, this first column, this is step size. So here in the column name, step. Now remember, this is a column name, but it's actually really the name of a list variable. So again, you can't leave blanks. So step underscore size. Okay, and maybe coming down here, let's see, a couple ways you could go about this. The step sizes here are 1/2, 1/4, 1/8. So it happens to be a very simple sequence there that we can do recursively, or we could even define a formula here in this formula box. Let's try setting this up kind of recursively and using the fill command. So that would mean, let's just put in the entry in the first box. The first step size is 1/2, so 1 divided by 2. And enter. Now here in this box, we'll start the recursive idea, and we'll say equals to. Now that cell that has the 1/2 in it is cell A1, so we'll say this will be A1 divided by 2, and enter. Okay, now come back here, select this cell, and now bring up the context menu, select fill, and now arrow down. Now there's 1/4, so this would be 1/8, 1/16, 1/32. Enter. Okay, they're all in there. Let's see, something else that has just occurred, and that's that when we start looking at these errors, we are going to want to have things easy to recognize and work with in our heads. So that means these exact fractions might be a bit of an obstacle for us. So let's go back and change this setting to be approximate to get decimal numbers for everything here. So back to the documents, settings, and let's go with the approximate calculations for here. Okay. Now, this column, this is going to have the Euler method approximation of y of 2. So let's give that a name. Let's see, Euler method. How about EM? Then underscore. I guess since Euler method by itself means approximation, we could say here Euler method and then y1 of with an underscore 2. Okay, and enter. Now, how are we going to get all those Euler method approximations to appear in our chart here? Well, without doing a lot of cutting and pasting, we could capture that variable as it changes. Let's try that. So here we are with we're in the formula area for this. And what we could do is go to the menu, go Data, Data Capture. I want to do this manually. And the reason is it seems that each time you even open the dialog box to an Euler's method, it triggers this capturing to automatically capture like nonsense. And so to avoid that, we'll stick with a manual capture here. Now, the variable we're capturing, that's that one we just labeled back on the graph page there. Let's just use the variable key to find that. Okay, we said that was the approximate y1 of 2. Okay, right there, that's what gets captured. And if you look in the bottom line here, the more complete instruction of this formula is elaborated here. This is the variable being captured, and the 0 means it's a manual capture. If the second part of the argument was a 1, that would be an automatic capture. Alright, so that looks like it's in order there. Hit enter. Well, looks like we're just about set. A little couple details here. I'd like to see the name of this column title completely there. Okay, there's step size. I'd like to see the name of this completely without looking at any ellipsis. Okay, that looks pretty good there. Alright, let's go back to the previous page. And, well, we know that this actually is an Euler's method approximation with a step size of 1/2. So let's go ahead and have that the approximation get captured. So we go here, Control, Capture. Okay, that should capture that one. And just to be sure, since that's our first one, make sure things are working properly. Let's go back to that page, see if it got captured. Yeah, sure enough, there it is. Okay, we're rolling. Let's go back here then, and let's bring back up that entry line for the graphing. Back here to the Y1, tab over. We see the parameters box is selected. Let's go to enter. And now we can tab down. Here's the thing we're changing now. Let's go and make this 1/4. Tab, enter. Okay, got a new value there. And we're just going to capture it. So again, it's Control, Capture. That's a manual capture. And now we see that we have the parameters edit box still highlighted, so just enter to go right back there. And we can once again tab down. Now we want 1/8 for step size. Tab, enter. Okay, we collect this one. Control, Capture. Got it. Once again, we can now hit enter because that will open the dialog box. We can tab down, make a step size 1/16. Tab, enter. Okay, let's capture that one. Control, Capture. And enter. Back to the dialog box. Tab down. Okay, 1 divided by 32. Tab, enter. And Control, Capture there. Okay, let's see if we got it all. Back to this next page. And it looks like very nice. Okay, we have all these various Euler method approximations of y of 2 with the step size recorded on the left column. Okay, I think I'd like to capture an image of this page, and then I'll maybe crop a little bit using something such as Microsoft Office, and then I will put it into the exercise set itself. So here we go. Capture that page. Do a little work. Okay, so there we are. Got our spreadsheet with just the 2 columns placed here. Step size and Euler's method approximation. Right now, we don't know too much about any errors here. We like to think that the error is becoming less as we're selecting a smaller step size, but we don't know too much just yet. When we do parts D and E, we will know more. So let's go to part D next. Okay, part D. Using the Nspire, obtain the exact analytic solution to this differential equation. Okay, let's try that. Alright, we were here. Let's see, to be solving a differential equation, we'll need to eventually go to a calculator application. Let's go ahead and first though, and let's go ahead and obtain the formulation of this differential equation. So let's go back to say here, where there's the entry space, and right here was the formulation of the differential equation already. Let's at least take this much here, and let's go with Control C to copy that. Now let's see, let's go and at the end of this problem, let's add a page and choose the calculator application. Alright, now let's see, this means we want to solve a differential equation. So that command, DESOLVE, differential equation solve, you can find it in the catalog. It's probably easier just to actually keystroke it in, as we've done there. And now we put in our arguments. The first will be the differential equation. Okay, so for us that's the y1 prime equal to, here's where we can take advantage of what we copied there. So now it's Control V to get that in there. Alright, now we got to put an A-N-D. The initial value that we know of, that was the y1 of 0 equaling 2. Okay, a comma. Now would come the independent variable x, then the dependent variable, the function name, and that's the y1. Alright, now this may not actually have an exact analytic solution, who knows, but we give it a try. But anyway, if it does, again, this differential equation solving command can be quite useful. You have to put in the arguments properly here. So you're supposed to use your differential equation and then any initial conditions that you know of specifically. Then it's a comma, independent variable, comma, dependent variable. Alright, well, let's see if this has anything for us here. Oh, okay. It does, but a lot of messy decimal numbers. You know, we should return to exact format here. So let's go back to our document settings and go back to an exact calculation mode. Okay. And if we go back up, and now push enter, and then enter again. Okay, that looks pretty good there. So a nice, relatively simple looking function is exactly the solution for y1. Okay, take a screen capture of that so I can put it in the exercise set answer block. While we're here, just to try out a little something with this claimed solution here, let's kind of test out a little bit before we do anything else. So for example, we had that initial value. Let's see if this function does that. Well, wait a minute. We actually don't have access to this function yet. After the solution there, it's just kind of sitting there with not being stored in any kind of function variable or anything yet. We actually still need to do that. So first thing, let's make that y1 there, that exact y1, into an actual function. Okay, so for us to create this y1 here as an actual function, we need to go further and define it. So what we might do is go back up here and enter, bring this down into this line, and then we can add on the other requirements. Now we're going to use the define command. See, as you finish typing the word define, it shifted from italics to plain text. That shows you have got a command put out there. And the way it goes is you can't just say y1, you have to give it its y1 of x. F of x notation is needed here to define a function, and otherwise we should go ahead and do that, and it's done. Okay, now that we have it defined as a function, we now have full usage of it, and one nice thing to do first would be to kind of test this out, see if it does a few things we're sort of expecting of it. For instance, how about that initial value? Does it really work? And so here we might do a y1 of 0 and see what happens. Okay, gave us 2. Another thing we might do before we go much further is let's take a look at our Euler's method approximations for a minute here. Okay, looks like okay, 3.35, 3.38, 3.39, okay, something like that. Let's see if the exact value is somewhere close to 3.39 or so, something like that. That would be encouraging to see. So here, let's actually see what y1 of 2 turns out to be exactly. Hard to compare that way. Alright, what to do? Let's get an approximate value by bringing this down to this line, and this time we'll go with a control equals 2 for approximation. Okay, 3.406. That's consistent with what we see going on there in our approximation tabulation. Good. Okay, so after a little cropping, there is a recording of our Nspire answer into this exercise set. Alright, now we have that exact function. Let's go to part E. Okay, part E. Return to the spreadsheet and provide a column which records the error of the respective Euler's method approximation of y of 2. Okay. So let's go back to our tabulation spreadsheet here, and now in this column perhaps we can record an Euler's method error. So that let's see, the name of this list here could be EM error. Okay, before getting this error column going, I want to make sure that this calculator is going to provide decimals here, not exact. So let's go back and check up on that settings and make sure that the approximate is going to be the result. Okay, what do we expect for the error? We want to take the absolute value of the difference between the exact y1 of 2 and the Euler's method claimed y of 2. Okay, so let's get that set up here. This will be then absolute value ABS, and in the parenthesis here we can say our y1 of 2 minus. Okay, now the entry in the B column in each case. Alright, so that can be done by using the column reference B and then a pair of brackets. So control brackets and then forward arrow to get out from the brackets, and then let's make sure we get that last parenthesis in there for the absolute value argument, and that looks like a good measure of error there. Let's hit enter, and there we are. Okay, let me just expand this column width a bit here so the title can be clear. Alright, take a screen capture of this. Okay, so here's the spreadsheet pasted here onto the exercise set question. There we have our step sizes in the left column, and the far right has the error we are now able to compute because of the fact that we have obtained an exact y1, which isn't usually possible, but it is here. And it helps us a lot to understanding this Euler's method and how it's working out so far. We do see that as the step size gets smaller, the error does indeed become smaller as well. Okay, question E continues. There is a popular, informally stated property of Euler's method. If you have the step size, you will have the error. does this appear to be the case in this solution? Okay, looking back at our step sizes, 1/2, 1/4, 1/8, 1/16, 1/32. Okay, there's a reason for that choice of step sizes in that each one has halved its predecessor. Okay, so now let's look over at the error column here on the right and see what happens. For instance, the first error in terms of thousandths, say. Okay, 219 thousandths. So what's half of that? About 110, right? And what is actually the resulting new error? About 106 thousandths. Okay, not bad. It kind of seems to be the case. If we go from that second error to the third error, the second error is about 106 thousandths. Half of that would be 53 thousandths. The actual new error, 52 thousandths. Pretty close to 1/2. Okay, and the next step from 52 thousandths to 26 thousandths, well, half of 52 is 26 thousandths. Actually, it is 1/2 in that case. And in the final transition, we go from about 26 thousandths to about 13 thousandths. Just equal to 1/2. Okay, so it looks like we seem to really have discovered or confirmed that that property seems to be working very well here for us. Okay, let's make a note of that. Okay, so there we are, having documented our discovery there as we sequentially halve the step size on the left. The corresponding error on the right column indeed appears to be halved as well. Okay, looks good. Okay, we want a graphic description of the TI-Nspire's Runge-Kutta method. If you have a graphic idea of what it's doing, it helps it make a lot more sense when you get into the algebraic formulation. So everything here is really approximate, but hopefully a visualization of the ideas will help a lot. The TI-Nspire's Runge-Kutta method has a similarity to Euler's method in that both of them use polygonal curves to approximate the solution. That is, they're both concatenations of line segments. There are two big modifications that the Runge-Kutta method has over Euler's method in drawing its line segments. One, instead of just a single slope at the starting point, as in Euler's method, the Runge-Kutta method will use a weighted average of several slopes taken throughout the step. Secondly, when the Runge-Kutta method has a proposed line segment solution, it's not done yet. It challenges that segment with another solution segment, and if the difference between these two proposed solutions differ by too much, we throw everything out, change the step size to something smaller, and start all over again. That's called adaptive step size. Okay, well, let's get started here. In the background, we've got a slope field for a differential equation, and this differential equation has an initial value point of -2, 1. In fact, we've even sketched the graph of the exact solution for point of reference there in the blue line. Now, we're zoomed in quite a bit here. The step size lies between those two vertical lines. Alright, let's get started. Well, since we have our initial value point here in the beginning of our step, that is the starting point for our line segment. Now we need some slopes to determine how to direct this line segment. One of the inputs to the slope average is going to be the slope at this point here. That's familiar, right? This is exactly how Euler's method starts off. So I'm looking at that slope field, and it looks like about there would be the slope. Now we're going to get ourselves a second slope to put into the average, and that's determined by taking the line segment that goes across the step size and has this slope. So take the line segment that starts here, goes in our first slope's direction, about there. And you know it's been drawn, right? That is actually an Euler's method approximation right there. But okay, for us it's just an aid to get another idea for slope. Okay, to get a second input for slope, we travel halfway across this line segment, say about here, and we use the slope field to get another slope. So according to the slope field at this point, it looks about like this direction here. Let me bring this over to the starting point to get it prepared for averaging. Now, in the weighted average of things, that very first slope we sketched is going to get a weight of 2/9. This one is going to get a weight of 3/9. Of course, equals to a third, but since it gets a 3/9, it needs to be 50%. I'm going to make it 50% longer than the first slope to reflect its greater importance in this average. I'll say about like that. Okay, that's two slopes. There are three slopes that are used to direct this proposed line segment. And now what we'll do is we'll lightly sketch in the line segment dictated by this second slope. Okay, so it's a line segment starting here, going in this direction, about like so. Now, as you recall, we traveled 1/2 way across the first line segment to pick up this second slope. Now we're going to go 3/4 of the way across this line segment to get ourselves yet another slope. Alright, so 3/4 of the way about here, and looking at the slope field right here to see which direction this slope is, it looks about, well, really very close to the other slope, isn't it? Okay, about there. Now I'm going to move this over here to the starting point. Now this would get a weight of 4/9. So I need to make this one twice as long as the first slope. Alright, about like that. And as it's turned out, two of these slopes are coincident. Time to sketch in the proposed solution segment. We're going to use the weighted average of these three slopes to do this. Okay, so we start here with our line segment now, and as far as this direction goes, okay, two of the most dominant slopes both have us aiming about like so, right? Now, however, there is still that third slope which is pushing us down somewhat in this direction. Now, again, the weighting is heavily in favor of where those first two are aiming, but it looks like about here could be a weighted average of these three slopes. Okay, now we have our proposed solution line segment. This could be the approximation. However, we're not done yet, because now we're going to challenge this approximation with another proposed solution line segment. This challenger line segment is going to have 4 slopes put into a weighted average. Alright, so for this 4th slope, go to the end point of this line segment and look at the slope field there. What will we have? It looks very close to a horizontal line, just a little bit negative slope perhaps. Alright, so now let's take this slope, ray, and bring it over here with the other 3. Now, the weighting of these is different than it was for the red line segment slope calculation. In this case, that very first line segment now gets a weighting of 7. So maybe I'll just extend that out to here, just so I can say, okay, there's a 7. Now the second line segment, it gets a weighting of 6. So I'm going to bring it out a little bit more, about there, and that'll be our second slope. The next slope, the third one, it now under this calculation gets a weighting of 8. 8/24 to be exact. And so I think I will expand this about there. The 4th slope we calculated, its weighting is 3/24. Okay, so it should be at least half as long as the first slope, let's say about there. Okay, there are our 4 slopes that go into calculating this challenger solution line segment. It starts here. Once again, let's kind of go in the direction of these 2, and they're fairly heavily weighted slopes to get us started. Okay, now that would be if there was just those 2 slopes there. We have a fairly strong influence pulling us down from that other slope. Maybe about there. But now there's that 4th slope, which is pulling us back up. Maybe say there. It's not heavily weighted, but it's definitely a very different direction. Alright, let's say there. Okay, that is the challenger solution, basically. Now, what we need to do is look at the end of this line segment and see if those 2 y-coordinates differ by more than the acceptable tolerance. Okay, we have a picture of the tolerance here I'll bring in. Okay, graphically there's a representative of the tolerance, that much. Well, those 2 y-coordinates exceed the tolerance. This means we basically throw everything out. It's not good enough. So because of that, here we are. We just threw all out, and what we're going to do now, remember the step size? It was out to this vertical line here. We make the step size smaller and start over. So maybe 2/3 or so of the original, like so. And then we would start this process all over again. In other words, go back here, get those 3 slopes, get their weighted average, get that first proposed solution line segment, create the challenger, compare the 2, and once again look to see if it is within tolerance or not. If it's not, we would throw all of even this out. Change the step size to be even smaller still, maybe 2/3 of this. And then try it again. Keep going until we get a proposed solution and a challenger whose difference is less than the tolerance. And then we accept the solution segment as being the Runge-Kutta segment. And then this process continues step by step by step. Although, as you see, the step size is changed all the time perhaps. Okay, that's the basic graphic idea. Part F. Use the Nspire to calculate several Runge-Kutta method approximations of y of 2 by using tolerance equal to 0.001, that's the default, and step size is delta x equal to 1/2, 1/4, 1/8, 1/16, and 1/32. You recognize those are the same step sizes we used in our Euler's method. Record these results into another column of the spreadsheet. Also, create a column of the respective errors of the Runge-Kutta method. How do the Runge-Kutta errors compare to the corresponding Euler's method errors? Okay, let's return to the Nspire. We were here, and we last calculated a column of errors for Euler's method there. Let's go to another column here and get set up to collect some Runge-Kutta method approximations here. And first let's name this column. Let's move over a little. And the name of this column could be, let's call it RK underscore Y1 of 2. Alright, enter. Let's see, how will we do this? Alright, we will use the method, Runge-Kutta method, on the previous page, and we can capture the y1 of 2 the same way we captured it for the Euler's method. So it's actually a chance to use a very similar instruction here in this formula bar. Let's go to the menu, data, data capture. Let's go with manual. And that variable we're capturing, okay, here in the variables key, it's right there, that approximate y1 of 2 there. Alright, that looks in order. Okay, I suppose something else we could do at the same time now, since we are also asked to get the errors of these approximations here. Let's go over one more column and put that here. So this could be the, we'll call it the RK underscore error. And the formulation, alright, same as we did for the Euler's method. Here we can use the absolute value, ABS, of, we can take the Runge-Kutta method quantity here, which would be over in column D in this case, right? So we can make a reference to column D with a D, and then over here with control brackets. And now let's forward arrow out of these brackets and do a subtraction. And here we want the known exact value of y1 of 2, y1 of 2, and another parenthesis to seal off the argument there. Okay, let's hit enter there, and we should be good to go. Let's go back to our page where we've been working with these approximations. Okay, let's tab up and tab to the right. And now we have the edit parameters key selected. We can enter. All right, now here we are. Solution method going to change to Runge-Kutta. There's the default tolerance we're going to keep at 0.001. Let's tab down. Okay, our step size, our first one, 1 divided by 2. Tab, okay. All right, got a quantity here. Let's capture it. Control, capture. Let's make sure it's working before we proceed with additional approximations. So let's go back to that page. Okay, sure enough, captured that y value and also computed the corresponding error. Great. Let's go back and continue. See, back up to the first differential equation y1, tabbing to get over to the edit parameters key, entering, and this time we're going to keep everything except changing the step size to 1 divided by 4 this time. Tab, enter. Okay, let's record the result. Control, capture. And let's go immediately back to the parameters menu here and tab down. And now let's go with 1 divided by 8. Tab and OK to go. Capture this result. Control, capture. And back to the dialog box. Tab down. Let's go with 1 divided by 16. Tab, OK. Record this result. Control, capture. And one more. Back to the dialog box. Tabbing down. Changing this to 1 divided by 32. Tab, OK. And let's capture this one. Control, capture. All right, let's look at the results here. Okay, so look at that. Each time, regardless of the step size, the Runge-Kutta method computed the same value here for its approximate y of 2. And notice the error is really quite small there, huh? We can help our table out here a little bit. Two things, by the way. First of all, you notice by capturing here, the other Euler's method also went ahead and captured those same numbers. So we can now kind of fix up our table here. We should really, let's delete these captures. And I wouldn't try to delete everything there because it ends up causing trouble. Just the fundamental deletion will take care of everything for us. Okay, there. All right, let's go back up to look at matters. And we would kind of like to make the important columns stand out. So you know what, you can go to the column reference C here, which is also a clickable spot. Bring up a context menu. You have a chance to pick a color, fill color. How about yellow? And do the same thing here. Here's a clickable spot. Call up a context menu. Color, fill color. Choose yellow, perhaps. Okay, and here we are. Easy to see. Okay, so evidently we have a Runge-Kutta method being significantly more accurate than the Euler's method, and that's one of the reasons we have this as one of the exercise questions, is that you don't want to just study Euler's method out of context. In the context of numerical methods, Euler's method is really just an educational method to get you to understand the basic idea, which is used in a much more complicated manner for the other much more accurate methods that are out there. So here we have our educational method, nice for learning, but when it comes to a real calculation, you want to be going with some of the much more advanced methods, and this Runge-Kutta method is supplied by the TI-Nspire is actually quite good. Okay, I think the last thing is I want to capture an image here to get all the columns in. I'm actually going to shift over to the computer view here for a moment. And this way. And let me extend this so the whole title is apparent here. There, now all the column titles are fully visible. Alright, and a capture image. Okay, and we can just return to our exercise set to finish up. There we see the table where in the fourth column are the Runge-Kutta method approximations of y of 2. And then we went on and have compared in the highlighted yellow columns the errors of Euler's method and Runge-Kutta. It's found that the Runge-Kutta method was significantly more accurate than the Euler's method. Take-home point here is that the Euler's method is, after all, an educational method to learn at first, whereas for accuracy in real calculations, you want to get familiar with some other method, and the Nspire has provided a Runge-Kutta method that is actually quite good and should be used for any of your real calculations. Okay. Question 1G. Identify the modifications that the TI-Nspire's Runge-Kutta method has added to Euler's method that yield such accurate results. Alright, we have two basic modifications. Firstly, a Runge-Kutta method calculates the slope value for its line segment from a weighted average of several slopes throughout the step. By contrast, Euler's method only uses the slope at the starting point of the segment. Secondly, the Nspire's version of Runge-Kutta utilizes an adaptive step feature. By contrast, Euler's method uses the same specified step size for every line segment calculation.